Hello everyone, this lesson is an introduction to variable acceleration, which is on page 181 of the book, and it will cover the first section, which is section 11.1, functions of time. Up to now, we've had particles moving with constant acceleration. That is, we go to here, when you draw a velocity time graph, we have this is velocity here and time here. Then the velocity increases at a constant rate, and you have a straight line. Now we are going to have the case where we have acceleration varies. So we might have acceleration going sort of like that, or maybe we have it going more like that. So this will be the velocity like that, and that be like that. Velocity and time. Here on this one, we can see that the velocity is increasing, but the rate of increase slows down, so it will be approaching a constant speed, perhaps. On the other hand, this one, the velocity is increasing, both increasing velocities, but this time it is acceleration is also increasing. The rate of change of velocity is increasing as well. Of course, when the velocity is constant, like that, we would use the Suvat equations. S equals ut plus a half at squared, v equals u plus at, v squared equals u squared plus 2as, etc. Those are relevant only for constant acceleration. It's a very common mistake for students to use those the equations, the Suvat equations, when the acceleration is not constant. When it is variable, there are never any marks for that. It's very important that you remember these equations are for constant acceleration only. So we'll see what we do when we have variable acceleration. Here we've got examples where we have acceleration varying with time. Here we have example 1. We just have a body moves in a straight line such that its displacement s meters from a point O at time t seconds is given by this expression here. S equals 2t cubed minus 3t when t is positive. Find s when t is 2. Well, that's simple. Just substitute 2 in here. S equals 2 times 2 cubed. That's 2 times 8, 16. Minus 3 2s are 6. So that's 10 meters. So the change in position, the displacement, is 10 meters. The time taken for the particle to return to O, well, what's happening there is that's when the displacement is 0. I think what would be happening is you have O, we are travelling on a straight line, and we would move up and we would move back, and then how long did it take to get back to the initial position? Well, that's when the displacement is 0. So as we can see here, we put 2t cubed minus 3t equals 0 equal to 0. Solve that equation, and we have a factor of t. So we have either t is 0 or 2t squared equals 3. So t squared is 3 over 2. So t is plus or minus the square root of 3 over 2. Of course, t cannot be negative. time is always positive, so the time taken to return to O is the square root of root 3 over 2. The solution t equals 0 is the solution for the beginning of the motion, because the displacement is also 0 at the beginning of the motion. This is a slightly different one here. A toy train travels along a straight track, leaving the start of the track at time 0. It then returns to the start of the track. The distance s meters from the start of the track at time t is modelled by that equation. S is 4t squared minus t cubed, where t is between 0 and 4. Explain the restriction t has to be between 0 and 4. Well, if t were to be equal to 4, you would see here we can factorise that by t squared, and you'll get t squared into 4 minus t. We'll put that over here. Well, the distance is from the start is greater than 0 because it's a distance. Distance is a scalar quantity, as it says here, so it must be, well, it must be greater than 0. It's essentially it's a magnitude of a displacement. Distances are always positive. So if that's got to be greater than 0, t has got to be greater than, it's got to be less than 4. And obviously t is greater than 0. So coming down to example 3, here we've got an expression for the velocity rather than the displacement. Of course, we could have displacement as it expressed in terms of time, we could have velocity expressed in terms of time, and we could have acceleration expressed in terms of time. So in this one, v equals 2t squared minus 16t plus 24. Find the initial velocity. The initial velocity is when t is 0. So substituting 0 into here, 0, 0, 24. So velocity is 24 meters per second. B, the value of t when the body is instantaneously at rest. Instantaneous rest, as I mentioned before, is when the particle changes direction. So it's like when you throw a ball up in the air, at the highest point its velocity is 0, because it changes the direction from going up to going down. At that point its velocity is 0, but it's only there for an instant. As it slows to 0 and then the speed increases again. So we call it instantaneous rest. And it's when v equals 0. So we put the expression equal to 0. 2t squared minus 16t plus 24 is 0. That is a quadratic. Well, we divide it by 2. T squared minus 8t plus 12 is 0. And factorise, we should be able to do that. T minus 6, t minus 2 is 0. So the body is at rest when t is 2 and t is 6. So instantaneous rest at 2 points. Then we have the value of t when the velocity is 64. So simply we put the velocity equal to 64, and we solve another quadratic equation. And this time t is 10 or t is minus 2. Of course, we can't have t is minus 2. T is always greater than 0. So the velocity is 64 after 10 seconds. And finally, the greatest speed of the velocity in the interval 0 to 5. Now, this really requires sketching the curve. It's a quadratic. We know from a quadratic, you have, okay, back to that. So quadratic, we know if t is 0, v is 24, so it crosses the velocity axis at 24. and we know already when v is 0, t was 2 or 6. And so we have the quadratic shape, 24 on the v-axis, 2 and 6 on the t-axis, and we therefore must have a minimum point at 4, down here. By symmetry, it's when t is 4. But we can find that out by completing the square, or of course by differentiation. So the question was the greater speed in that interval. Well, the greatest speed in that interval we can see between sort of 0 to 5. Well, 5 is here. So the greatest speed was in fact 24. It never got greater. Oh, I've done that again. It never got greater than 24 in the integral 0 to 5, which is around about here. So closing that, going to the next page. Right, rate of speed is 24. Okay. Next, I suggest that you look at exercise 11a. This is on page 184, and do some of these questions. You've got 8 questions here, and they are all involving expressions for displacement or velocity in terms of time. Doesn't look like we've got any with acceleration in terms of time, but they will be good practice. Next video, we'll move on to how we deal with finding displacements and velocities and accelerations when we've got any one of those, and we'll use differentiation. We'll be using differentiation and integration. Next video will be on differentiation.